Analog microelectronic circuits class. So now we are doing op-amp, this operational amplifiers and the applications of it, and we covered amplifiers, different types of amplifier configurations. Then we looked at precision rectifiers, and then we have come to the special category of circuits called as oscillators. In the last class we discussed, and I hope you understood about the principle of operation and the criterion which we need to satisfy to produce oscillations. And we also looked at the first circuit, which is RC phase shift oscillator with the using op amps. So in today's class we'll continue our discussion to another class of oscillator. We call it as Wienbridge oscillator, and the name the name of Wienbridge is because of the use of Wienbridge proposed by a scientist called as Max Wein. So due to that we call this as Wienbridge oscillator. Alright, now this is actually a very simple and a stable oscillator, and if you remember we were talking about the classifications of oscillators, where I mentioned that there are oscillators at audio frequency, there are oscillators at radio frequency, and so on. So this is one of a very stable audio frequency oscillator, and straight directly coming to the circuit diagram of this. So in the RC phase shift oscillator, what we have done is, or the proposed architecture was, an amplifier is there. An amplifier, we used an inverting configuration. So for 180 degree phase shift, to compensate that, we have used the other 3 RC networks to get another additional 180 degree phase shift, so that the total phase shift around the loop becomes 360 degree, right? So here the configuration is slightly different. Here we have we use an op amp, but we are not going to use this op amp we have to consider. So two things, when an op amp is there, we have to consider two things. One is we need some gain, that means an amplifier part should be there, and the other part is a feedback path, right? So here the configuration is slightly different from what we have done for RC phase shift. Here we use this path, which is your in this mode. We use a feedback, we'll call this as RF and R1, right? And the moment we use this kind of thing, it is resembling a non-inverting amplifier feedback configuration, right? So this will be the output, and we are not feeding, there is a feedback resistance over there, but from the output we can see one more path where we establish a series and a parallel RC network. So this is one RC from the output, and we have one more RC which is connected in parallel. This is how the proposed circuit of Wienbridge oscillator is. So this is R and this is C. Right. So now when you look at this circuit, we can see two things, right? One is you can clearly visibly you can see an amplifier part, right? Here you can see very well, you can see an amplifier, but you can also identify the amplifier configuration is a kind of non-inverting type, because this is in the non-inverting type only we will have this kind of structure where we provide an input to the positive input terminal. On the other hand, you can also see here a series and a parallel RC network, which in this case act as the feedback network. So this is a series RC and this is a parallel RC, right? Now looking at the circuit, you can visualize, or you can see that there is both positive and negative feedback in this, right? And you can see here is a negative feedback output back to input through the resistance RF, and this is basically for the amplifier, or this is for stability in gain, or this feedback will ensure stability in gain, By providing by fixing the value of RF and R1, the gain of the circuit can be stabilized. Now you can also see the other feedback from output back to the positive input terminal, where which helps, or this is something which helps in oscillations. Or oscillations are sustained through this series and parallel RC network. Now we know that from the principle of oscillation, from the principle of an oscillator, and a circuit can oscillate under two conditions, right? So we mentioned that A beta should be equal to 1 angle 0 or 360. This is a condition what we wrote for sustained oscillations, and we also mentioned that this condition can be A beta should be equal to greater than or equal to 1 for the oscillations to start and then to stabilize, right? So as far as the circuit meet this condition, or when A beta equal to 1 and the phase shift around the loop becomes 0 or 360, if we satisfy that condition, definitely we can say that the circuit will oscillate, right? So to have a detailed look, or to see how this arms, or how this forms the shape of a Wheatstone bridge, what we will do is, let me redraw the circuit. Let me just redraw the circuit and see. This is minus and I'll draw it the other way. This is plus and this is minus, right? Now from here, so here this is your output terminal V out, and here if you look at this, from plus to output you have a series RC. So I am just redrawing that R, and this is C. Now from the same point, that is from this point to ground, you can see there is a parallel RC. So I will consider this as a ground point. So from here we have a resistance, so here we have series resistance, and we also have a parallel RC here. Alright, now look at the other two branches. So what we have done is, this is RC, this is also RC, and this point is, this is this point. So let me mark this node here, so we will get to know this is this node. Now look at the minus input, look at the minus terminal. From the minus terminal to output you have this resistance RF. So from here we have this RF, this is RF, and then again from the same terminal. So if I use a different color here, this is this node. So from this terminal again to ground we have this R1, right? So this is R1. This is how the appearance is like. So you can see that this is the series RC and this is the parallel RC. Now what we will do here is, you can see that the feedback network is actually connected in the form of a bridge, right? The feedback network is connected in the form of a bridge, whether it is towards the negative input side or towards the positive side. It is actually in the form of a bridge, and this bridge is called as Wienbridge, right? Now and this bridge consists of, as you can see, the bridge consists of a series RC network here and a parallel RC here, and the other arms we have this RF and R1, right? And the bridge is connected between, you can see that the bridge is connected actually between the input terminals of the op-amp. Now as I mentioned before, the resistors RF and R1 will provide the gain stability, and the series and parallel combination of RC will provide zero phase shift in the loop, and thereby we can say that it will give you oscillations, right? So now we know that the phase angle criterion for oscillations is the total phase shift around the circuit must be equal to 0. But you can see from here output through this RC, so since this series and parallel RC is meant for meant for the positive feedback. You can see that the output is fed back to the positive input terminal. So we cannot see any phase shift over there because it is connected to the non-inverting input terminal. Now it purely depends on the value of RC what we choose, right? So depending on the value of RC, we can say that the total phase shift can be made equal to 0. So what we will do now is we will go ahead and analyze. I hope the basic circuit is clear. Now we will go ahead and analyze the circuit and come up with the condition for oscillations, which will give you more clarity on how this works, right? So similar to what we have done for phase shift oscillator, what we do here is we'll first we'll consider only the feedback network. We'll look at only the feedback circuit. Can I get some response in the chat window? Are you guys with me? Alright. So when I say the feedback circuit, I am looking at the positive feedback side where you have a series RC, which is from this is the output point, and we have a parallel RC, and this is given back to the positive input terminal. So I'll mark this as the feedback VF. So this is RC, this is R and C. Look at this. This point is output and this point is considered as the feedback point because we are looking at the positive feedback mechanism. Alright. Now in a similar way how we analyzed the phase shift oscillator, we will analyze this by considering in S domain, in Laplace domain, where we can write this as, instead of writing it as C, I can write this as 1 by SC, and this also can be written as 1 by SC, and whatever analysis we have done, the same way we will do. So now you can see this part, this is a series RC, so which can be written as a series impedance, right? So ZS I can write. Now what we have here is a parallel RC, right? So this can be written as a parallel impedance ZP of Z. Now what is ZS series impedance? It is R plus 1 by SC, or this can be written as 1 plus SRC divided by SC. This is your series impedance. What is a parallel impedance? Parallel impedance is R parallel 1 by SC, which can be written as R into 1 by SC divided by R plus 1 by SC, which can be further written as R by 1 plus SRC. This is the parallel impedance. Now what we are trying to do here is, what we meant by analysis here is, we will write the condition A beta equal to 1, right? Or we know that the condition for oscillation is A beta should be greater than 1 with the phase angle of 0. So that condition we will try to apply here. So for that, first we will write the feedback voltage VF. How can I write feedback voltage VF over here? From the output, a fraction of output is coming back to feedback. So how is it coming? You can think this as a voltage divider network. You have two impedances here. This is ZP and this is ZS. So we can write VF of S as ZP of S divided by ZP of S plus ZS of S into V out of S. So this is the relation, right? Now in this we can substitute whatever we have written here. One second. Yeah. So when we substitute that here, we can further write this as VF of S is equal to ZP. ZP is R divided by 1 plus SRC divided by R divided by 1 plus SRC plus ZS is 1 plus SRC divided by SC, right, into V out of S, which can be, let us simplify this denominator 1 plus SRC we can cancel, 1 SC will come to the numerator, so numerator becomes SRC divided by denominator we have 1 plus SRC the whole square plus SRC into V out of S. Alright. Now, what we got here is the relation between the feedback voltage and output voltage, that is identified as beta, which is Vf of S divided by V out of S, which is equal to SRC divided by, if I expand this bracket, S square R square C square plus 2 SRC plus 1 SRC is 3 SRC plus 1. I hope this is clear. This is just a mathematical analysis what I am doing. So this is what we have as the beta factor, right? Now so let me just keep this, because this I need anyway. Now, so this what we have done here is the first part where we analyze the feedback circuit. Now let us move on and analyze the amplifier part. Let this be here. So let me analyze the amplifier part. So in the amplifier part, if you look at the amplifier, this is minus plus. At plus you have an input which is Vf of S. Then there is a series, the feedback resistance and the input resistance. This is V out of S. This is RF, this is R1. Now this will give you the gain. Gain can be written as 1 plus RF by R1. What is this gain? Gain is V out of S divided by Vf of S, considering Vf as the feedback voltage, right? Now finally the requirement for oscillation. So what is the requirement for oscillation here? The requirement for oscillation is A beta should be equal to 1, right? So if I look at that, look at these two expressions. So let me put this as equation number 1 and this as equation number 2. Then I can write what is this A beta. So if I write for that condition, I can write it as A is 1 plus RF by R1 into beta is SRC divided by SRC the whole square plus 3 SRC plus 1. This should be equal to 1, right? Once we arrive at this condition of A beta equal to 1, what we can do is put S is equal to j omega and equate real and imaginary part. Real parts, equate real parts and imaginary parts. So which will give you the condition for oscillation, the expression, the condition for oscillation as well as the gain requirement of the circuit, right? So if I continue this analysis and if I write further, I can write it as I'm just taking the same relation. So it is 1 plus RF by R1 is the A part, 1 plus RF by R1 into if you look at here, you have SRC and the rest things we can take to the other side. So S is j omega RC, and towards the other side SRC the whole square. So it is minus j omega RC the whole square, which is j square minus. So it is minus still there, R square C square omega square plus j into 3RC omega plus 1. This is clear what I am doing. I have just taken this denominator to the right side. S square is minus, then omega square R square C square plus the remaining terms I have written, right? Now once this relation is obtained, what I can do is I can equate the real part. So when I equate real part, left hand side you have What do you have here on the left hand side? Nothing is there. So when I equate real part on from the right hand side, I can say 1 plus r square c square omega square is equal to 0. Not 1 plus, it is 1 minus. Or I can write omega square is equal to 1 by r square c square, or omega is equal to 1 by root rc. Further, we will write this as frequency as 1 by there is no root, omega square, right? Yeah, is 1 by rc, 2 pi rc. This is the frequency of oscillation. Now after equating the imaginary part, what we are expecting is we will get a condition for the gain requirement. So on the left hand side we have 1 plus rf by r1 into j omega rc. On the right hand side what we have is j into 3 rc omega. So everything will be cancelled. What is left out is 1 plus rf by r1 will be equal to 3, or which implies that rf by r1 should be equal to 2. Still we can write rf is equal to 2r1. So this is the condition what we need to meet in order to have the proper gain in the circuit. So what we have done here is we started with the circuit of Wienbridge, right? So Wienbridge circuit, and we know that there are both feedbacks exist here, and we are looking at the positive feedback condition. We force the condition, we ensure the condition for oscillation, and that is done in the circuit with the help of a bridge. And for analysis we have considered the feedback path and the amplifier part separately, obtain the gain and the feedback factor A and beta. Then we wrote the requirement. So if such a circuit can oscillate if it satisfies Barkhausen criteria, that is the condition what we have. And now if the Barkhausen criteria is satisfied, the circuit can oscillate. So to obtain the condition for the circuit to oscillate, there are two things. One is the condition for gain at the frequency of oscillation. So at f is equal to 1 by 2 pi rc, the circuit should provide a gain, or 1 plus rf by r1 should be equal to 2, right? So this is the circuit and analysis of Wienbridge oscillator. So if you have any questions based on this, you can ask now.